Cool. Yeah, welcome to the third lecture of the series. Today we'll be talking about dynamics mostly. Linear, rotational. We'll start with linear first, give some intuition, and then talk about rotational stuff. And then if we have time, we'll talk about energy. But if not, there's gonna be some problems listed in the handout. I mean, we'll give a brief introduction lah, but it's gonna be quick. So, right. So today we'll be talking about dynamics. Dynamics. And specifically momentum and energy. Right. So um, to summarize, the whole of dynamics starts with momentum. Like the whole idea of like how things move comes from momentum. Because in the previous week we were talking about kinematics and stuff, right? Like we were talking about how things move, how you can model things, trajectories, stuff like that as kinematics, like how you describe things with math. But if you want to relate it to the real world, when you want to relate it to like things that you can measure, that you can like see in the world, and you want to predict things, I mean, yes, you can I mean, so there's two different pillars in mechanics. There's kinematics and dynamics. So kinematics tells you how you can model and describe things mathematically, and then you can from that you can describe velocity, describe acceleration, describe different frames of reference. But then in dynamics, you start to define how things move. You define mass, you define force. So specifically, inertia and force. So these are two different pillars. One pillar of kinematics is different from the other pillar of dynamics. Um, so this is just much more abstract. So let's start with momentum. When something moves, we say that it has momentum of normally we call it P lah. Um, I like to use vector with this like up arrow notation. Um, and momentum p for an object with mass m and velocity v, then momentum is p equals m times v. So this kind of makes sense because if you define momentum to be the moving feeling that you have, um, so suppose you're not sure if you guys have driven a car, but let's say you were riding a bike versus riding a scooter. Like one of those like two-wheel scooter, like the ones that you like push with your feet, like kind of like a skateboard. Okay, let's talk about skateboard and a bicycle. So if you're on a skateboard and you're on a bicycle, the bicycle is much more heavier, right? Um, so it, like so it, definitely you feel more mass. So even though you're going at the same speed, the bicycle has more momentum in a sense because it has more movingness to it. Um, Another way to put it in a more intuitive term is to say that you need like it takes more to stop a bicycle than to stop a skateboard. Maybe like the difference between a skateboard and a bicycle is not that bad. It's not that big yet. But suppose let's say a bicycle and a truck, even though they both can go at the same velocity, um, the truck definitely has more. You need more movingness to move truck, right? So yeah, it's very abstract, but I think like it's a good intuition to have. Like momentum is just that moving feeling. Um, so see, now that we have momentum, the way we relate it to force is through Newton's second law. Um, once upon a time there was this guy Newton, and he was like, um, yeah, given this momentum, I can actually like define something called force. Um, and the thing he said is that like forces don't really matter. The net force is what really matters. The net force acting on the body is going to be the rate of all forces acting on the body make it move, is what this equation says. If you take some object and you exert forces on it all over the place, like it can be like gravity, drag force. We'll look at an example soon. But if you take all the forces act on something, the resulting vector would be dp dt. The resulting vector would be dp dt. Cool. I think so far it's just mostly review for most of the people here. Um, but I do want to say that. I don't want to make the distinction clear that like forces are something that people made up. It's like you can't really point at something and say, "Hey, that's a force," because so force is something that Newton made up, and we're kind of stuck with until now. So, and also one more thing is force is dp/dt. Even though it's tempting to say F equals ma, it's not always ma. So if you've taken calculus, you realize that this is d and v dt. So if the mass is constant, then it's ma. If the mass is constant, then it's ma. It's not always mv. Cool. Let's look at a problem where we talk about the use of F equals ma. So, more importantly, if you go use a mechanics textbook, they will really a lot of problems will look like this. So, let's talk about a simple problem. Draw it bigger. Okay, so we have a mass m1. We have a mass m2. Oops. We have a mass m3. And someone asks you like, hey, how does this thing move? If you just let this play in time, how does this move, after I release it? So this is something called an Atwood machine. So it's one of those like theoretical problems where someone like it's one of those things where people like cook up for to like test people if they know how to use F equals NA basically. It's really I'm gonna say that like I don't okay maybe if you take a mechanical engineering class or like maybe if you go into engineering you'll see this more often, but uh this is more one of those like toy problems where you exercise your use of F equals NA and see if it aligns with what you expect. Um so do you guys want to solve this together? So we can do this together. Maybe I'll like stop talking for like a few minutes and see what you guys come up with. Or actually, if you guys have any ideas on like how you should start on this, like, I'm happy to take suggestions as well. Suppose you're given this problem, you want to find the acceleration of all these three masses. So you want to find A1, A2, and A3. How would you go about doing this? Okay, so hopefully you guys have had time to think about it. Um, can someone tell me like how if I just want to express A1, what equation should I use just right away? Should be quick. No one? Okay, sure. So if I want to use oh sure, yeah. So there's tension and gravity. Right, but like way before that, I know that I want to write acceleration, so I need like the sum of forces on F1. And so th from there, I will have to talk about tension and gravity. So thank you, Jungwon. Um, so suppose I call this tension T1, I call this tension T2 and T3. Oh sorry, T2 also, because they're the same rope. Um so One more thing is that let's define this as x equals 0 on the wall, and let's define x going down to be positive. So from kinematics, we know that it doesn't really matter like what direction you choose, as long as you're consistent, as long as you stick to the convention, the result you get should be right, up to a minus sign. Um, so that should be a bigger physics thing that you should keep in mind. It doesn't really matter if you choose down to be positive, up to be positive, left to be positive, or right to be positive. Like as long as you're consistent, all the math should work out. And yeah, just keep that in mind. Because the world doesn't care how you describe it. The world just is. So um M1A1 is equal to sum of forces on mass one. And so since we choose down to be positive, we have gravity and then tension. I use a minus sign because tension is pointing out here. Same thing for M2A2. Same thing for M3A3. Cool. So we're really close to getting what we want. However, we have these like weird T1, T2, T3 terms. How do we take them away? So one thing that we can do right away is notice that the T3 is just T2 lah. Like, so okay lah. I mean we still have like two unknowns. Actually no, we have one, two, five unknowns. So we have the three unknowns that we wanted to find. We have the three unknowns. So three unknowns plus these two. So we have five unknowns in total. Right now we have three equations already. We just need two more. So in these sorts of problems, as what Brandon says, what we would need right from this point on is the conservation of string. But I don't want to jump into it right away because I want you guys to think of the bigger picture here. Because it is true that we will use conservation of string in a while, but why we want to use the conservation of string essentially is the constraint of the system. So in this problem, the constraint is the conservation of string. In some other problems, the constraint might be the sum of displacements. It might be some elastic, uh, like for example, if you have a thermal expansion problem, um, well, maybe thermal expansion is a bad example. Let's say, suppose you have an elastic problem, lah. Suppose you have like um, some mass here and then a wall, and then you have like two bars that can like extend or deform or like. So in this case, then you will have to think about um the sum of the displacements of these two bars will be the same. Um, like it depends on the problem you have. So what I'm trying to say is that when you have like more unknowns than equations, you should start looking in the constraint side of things. Um, sorry, that was a really weird example I just randomly brought up, but it was in one of my homework problems. So um, so yeah. Anyways, so there's two things that feel like we could need. Um, so one thing is on this pulley. S- Oh, sorry, my phone just went off. Great. So one thing is on this pulley. My phone's going off. So this pulley actually has a few forces acting on it, right? But then again, if you look back at the if you look at the problem, these pulleys are not moving. Only the masses are moving. So for the pulley to not be moving, the sum of forces on it must be zero as well. Um, so right away you can write. So the first constraint being that the pulley doesn't move says that T1 is equal to T2. So yeah, cool. We have one equation. We've reduced it down to four unknowns. Hmm. What else should we use? Well, something else I realized is oh, okay, wait, I think that's okay, now we can use this conservation of string. So how to use a conservation of string? There's a few ways. So I mean there's two approaches lah. I'll show you the first approach and the second approach is more tedious. So for the first approach, you you will realize that if you displace n1 by x, so if you push n1, actually like let me push it downwards. If you push n1 down by x, gosh, my phone. Um, and T2 and T3 also go up, right? T2 and T3 go up. Um, but okay, wait. Let me talk about a longer way first, and then like we can talk about this. So the conservation string goes like this. So if you have this length here plus these two lengths here, they don't change. So um, you can write M1. So um, suppose I call this a D, and then this L1, um, and this should be L2, L3, and then there's a uh, pi R, pi R. So like the circumference lah. So L1 plus pi D plus L1 equals plus L2 plus pi. Yes. So my bad. So that was confusing for people to see. But yeah, so at the start, I'm just adding all the lengths of the string together. So um there's an L1 part here, there's a pi R, and then there's also another L1 here. Um, and then if you add these two as well, um you will get this total equation. So there's a reason why I use like L1 for both of these because like there's no mass on the right hand side. I mean there is a mass on like M2 and M3 lah, but um for um for M1 since we call it L1, so that's why this is also L1. In hindsight, L2 and L3 are the same, but you'll see soon that like we will arrive at A2 plus A2 and A3 are negative. So we'll arrive at that conclusion. So it is true that L2 and L3 are the same, but the magnitudes are the same. So let's see. So this is the concept of a string, and then so let's take the second time derivative. Let me just simplify this for a little bit. 2L1 plus L2 plus L3 is equal to L total minus 2 pi R. So the R is just the radius of the polyla. Okay. So now if you take the second time derivative, you'll get 2A1 plus A2 plus A3 is equal to 0. So that is our conservation of string equation. We can put it here. 2A1 plus. Okay. So I think we have most of the ingredients. We can start to put things in. So I think for now I'm just gonna find A1 because you can also find A2 and A3 lah, but I'm just gonna find A1. But before that, is it okay? Is it clear how we got the conservation of string relation? There is another way that I was alluding to just now, which was just to skip all this like math that you write down, and you just like displace M1 by a little bit, and then you see like you displace like M1 by like going down, and then you see how M2 and M3 change. But then again, I feel like that's I think this method is more illuminating lah. You see like why there's a two here like right away because L1 and L1 add together. Um, so yeah, I think this method is more illuminating. It's up to you. Um, so yeah, the other method was displace it and then see how much these go up or go down, depends. Um, yeah, so okay, now let's start solving it. So suppose I call, so let's, okay, I will start with this equation. A1 plus 2A1 plus A2 plus A3 is 0. And then from here, can say G minus T, G minus T1 over M plus G minus T2 over M. So I can write this, and then I can simplify. T2 is the same. The 2's I can cancel out. There's a 2G. Um, shit, my bad. Wait. Hold on, my bad. I cannot just do that. I realized I forgot to write M1, M2. Sorry, my bad. You did not see that. So this is G minus T1 over M1. Forgot to write M1. Then G minus T2 over M2 plus G minus T3 over M3. Okay, okay. That should be right. So 4G minus uh 4G minus so 2 plus so minus 2T1. 4T1 over M1. Sorry, 4T2 over. Okay, now we're there. So from here you get T2 is equal to G over 1 of M1 plus 4M2 plus 4M3. And that's the final answer. For the tension, is it too small? Oh, okay. I mean, oh, sorry. I took a second time derivative. So I take a second time derivative. So if you take the time derivative, these are constants because we say that the conservation of string holds, like the string doesn't change in length. So if you take the time derivative, the total length doesn't change, the 2 pi r doesn't change. What does change is L1, L2, and those lengths. And specifically, those will be the accelerations of those masses. So yeah, thank you for catching me there. I wasn't too clear with that. Yes. So, okay, so that's the tension. And from the tension, we can plug it back into our original equation, and then you can find A1, A2, you can find A1 is equal to G minus, so T1 is twice T2, so 2G over M1, and just this reciprocal. Cool, yeah. So that's How you can do these types of problems? Essentially, you write down F equals MA, and then like constraint problems, the constraint equations, and then you should find the answer. So I think we spent a lot of time on that. But I just really wanted to drill home the problem solving aspects of this. Right. So that was Newton's laws. Um, and that was the second of all three Newton's laws. Let's recap what we did. We defined momentum. We used Newton's second law because it's a law, so we just kind of used it. You can derive it when you take like higher mechanics, but yeah, you still make some assumptions. Um, and then yeah, we also talked about example problem. So now let's talk about another example problem where you can really see Newton's laws shine. So this was Newton's second. There's also Newton's first and third, which I think ties into the idea of like center of mass and center of like momentum, like more naturally. So Newton's first and so Newton's first says that inertia is a thing, and then Newton's third law is the karma law. So inertia thing. So like what I mean with inertia is that when you stop something, uh, when something's moving, it will try to keep moving because it doesn't want to change its path. If something's not moving, it will just spontaneously move because it's inert there. It's not gonna move. Um, so yeah, like it's the law of inertia. And then its third law is the karma law because like if you push someone, you also feel pushed. If the object accelerates, so if an object exerts a force on another object, the other object will exert the same force back on the original. So it's the karma law. So that's really abstract, but I think if we talk about center of mass, this would look more defined. So what's the center of mass? Center of mass is a great idea for when you have like many different particles. So suppose you have a particle here, particle here, particle here, particle here, and then you want to describe how they move. Um, so right away you were like, oh, like I can do F equals MA for one by one on all of them. But if I want to just ask like how do all of them move? Like the aggregate statistics, like the aggregate movement of all four things, not just individually. Then you could talk about center of mass. So it's defined like this. It's the center of mass is the weighted sum of the masses. So total xcm is equal to the sum of mi xi. So it's kind of like statistics. Or let me just rewrite it as like this. So the total mass is just the sum of the individual masses. So this should remind you of statistics, right? This is just a mean with frequency m1. So mi. And xcm is just the mean, the weighted mean lah. So why is this important? So Newton's first law says that because of inertia, things that move will keep moving. But then there's a trick. So the trick here is to talk about instead of individual particles, you're going to talk about the total of all of them. So this will be kind of, I mean, assuming all four masses are the same, I just kind of eyeball the center of mass here, but it should be like around the middle of all the four masses. So I think it's around here. Yeah, assuming all four masses are the same. Um, and so the cool thing about this is that you can say that this essentially has four n. So it's supposed to call this n. So you can just say that okay, that point is now like there's a mass of four m there. And all forces acting on the system act on this. So all forces acting on the system now act on this. So this is assuming that um, yeah. So because like individually, you can write this right for each mass, and if the accelerations are the same, then you can write if the accelerations are the same, then you can add all the equations together, and then you will still get a net force on all of them. And then on the right hand side, you'll still get the mass, but it's now the mass of all of them. So essentially, F equals ma still works, just that now you have to use all the forces acting on all of the masses to be the net force, and that net force would act on this point here at the center of mass, where that point has like 4 m, the total mass. So that's the key idea here. And then Newton's third law says that if you do this now, so Newton's third law says that okay, it's valid to do this. Why is it valid to do this? Suppose there is a interaction between M1 and M4. Right, suppose there's an interaction between these two guys. Can I still use this? So the answer is yes, because Newton said so, and that's in Newton's third law. So Newton's third law says that when we're doing this suspicious sum, it's some terms cancel out. So specifically, these two forces are equal and opposite. So in the sum, they will have this like plus F, and then on the right hand side there's also like a minus F. So if you take the whole system as a if you take all four particles as a system, they cancel out, and this still holds. So that's Newton's third law for you. Is that okay? Any questions at this point? It's kind of a funky concept to wrap your head around. But yeah, so let's look at the problem. So wait, suppose you have a person on a boat. On one end, the person has mass n, the boat has mass big N, and length L. When the person moves to the front, the boat will be displaced leftwards by a little bit. So find this shift. So find this shift. D lah. So what is D? Okay, so you guys get a setup. So we have a boat of mass big N and total length big L, and one person of small mass N walks from one end to the other. Look, now the question is, what's the displacement of the boat? So do we have any takers for this problem? Any takers? So like, let's think about it for a second, and then we'll discuss it in 9. Think about it for like 3 minutes. I'll come back. Okay, cool. So hopefully you guys have had time to think about it. The reason why I really want you guys to think about this is that once you've struggled with a problem, you really learn how to like the nuances and like the little details, you know. For example, here, I think the conservation of string is one of those things where like, oh, of course it's conserved. But then like once you actually write it down, you'd be like, what length should I use? I'm not sure. So yeah, so let's try to try to struggle with a problem as much as you can. Because what is life without struggle? So the key idea here, since we were talking about center of mass and like Newton's third law, essentially this problem is a center of mass problem. So the idea here is that like there is okay, so suppose that because it's like everything's floating around, right? Like I think it's easy if I define a shore here. So suppose I call this like shoreline, like as for example as um so yes, like that's what Isaac said. So Isaac said that is the center of mass always constant when there is no external force? Yes, because and but then there's a more general idea here because there's I don't know yeah, yes, that's true. No external force is a good condition to say for the center of mass. Yes, Newton's first law. There is there might be internal forces. For example, the boat might have some friction with the mass or with the person, big M. But it doesn't matter because it's all internal forces. The internal forces don't really matter when you talk about the center of mass. Um, so yeah, like when a person walks to the front, their feet, you know, like when they put their feet one in front of the other they kind of push the boat like backwards a little bit, little by little bit. So suppose I call this person and this boat X person, X boat. Oops, my bad. Not sure what that is. Actually, no, wait. Let's just call this X boat. So X boat, and then there's just X boat plus L. Right. Actually, you know what? I'll just call it X naught. It's easier. So there's so the center of mass would be at a place where it's M plus big M over M plus M. So that's the center of mass. So after this is gonna be x naught plus d, right? This is gonna be x naught plus d. Oh, sorry. I think one more thing that I should have done is that to talk about the center of mass of the boat. So the boat itself has a center of mass in the middle. So I was almost sorry, yeah. The boat itself has a center of mass at the middle because the boat because if you don't talk about this, you say oh the boat has the mass total mass here. But the boat doesn't have the mass there, right? The boat is uniform. I mean, like, we didn't really say that, but you know, like of course it's a valid assumption. Um, because the boat has equal mass all throughout, so it's essentially all the mass acts through its center. So instead of using x naught, we should use naught plus L over 2. This is the center of mass. So after the person moves to the front, this is gonna be m x naught plus d. And this is the new center of mass. Okay, so now it's just a problem with algebra. I can't fit it there. Anyways. Yeah, now it's just a problem of algebra. So I can cancel both sides. Um, Yeah, so there's an M X naught on both sides. It's big M X naught plus L over 2, big M X naught plus L over 2. This goes away. Right, I kind of just did all the math like right away. I just cancel it on both sides. So finally, you get D is equal to small m over plus m. L. Cool. So that's how you use the idea of center of mass on this kind of problem. Because there's so when it's kind of because if you use the free body diagram approach, it's kind of like what forces is there, right? Like if you want to look at the boat itself, like it's gonna be hard to do that. Like you could still do that if you like make some assumptions of like the person exerting constant momentum, like suppose the person walks at constant velocity, so they have they exert like um momentum on the boat. Then you could integrate that, and then you could get like the total. You could do that, but it's gonna be hard. Um, More easily is to notice that since there is no external force, the center of mass is not gonna move, and you just equate the initial and final. Would you just say that like, around this point is where around here, I guess. Around this point is where the center of mass lies. Yeah, something like this. So okay, let's look at if our equation makes sense. Because in our first lecture, we had talked about dimensional analysis and um like it's like to think about how you could skip steps in a problem, how you can describe complexity. So I guess it's a good skill to use now. So let's look at the final expression that we had. Um, the units wise, does it work out? Yeah, unit wise it works out because it's mass over mass times length. So it's just finally this is just units of length, which makes sense. Um, so one more thing is, does this scale correctly? Does this scale correctly? So if the person is massless, if this person has no mass, the boat will not feel any momentum from the guy, right? Or equivalently, you can see that the person doesn't have any influence on the center of mass. So that's why D would be zero, which makes sense. When small m is equal to zero, D is also equal to zero. Okay, so and suppose the boat is like infinitely heavy. If the boat is infinitely heavy, the boat is infinitely heavy, then it won't move, right? The boat would just be like a floor. The floor doesn't move. The floor is the floor. So this will also be zero because this thing goes to infinity, D goes to zero. So yeah, that will make sense. So I guess like a good thing to have is to let me just mute my notifs. Sorry, 'cause my phone's blowing up for some reason. Um yeah, a good thing to have like whenever you derive a new formula is to think about does this make sense? Like it should like at this point be built into the OS lah. Be built into your operating system. Like you should always like ask yourself like when you finish a problem, you should always ask yourself, does this make sense? Like how does my gut feel with this? Like do I agree with this? Okay, so any questions thus far? Okay, one last thing before I move on. Momentum is like a currency. So so I'm just gonna use the example of a body falling in a drag. So suppose there's a drag for suppose you have a body like that's falling in the atmosphere. So it will have some gravitational force exerting on it, and it will have some drag force exerted on it, right? So like the reason why I bring this problem out is um so if you have something dropping from the atmosphere, we know that it reaches terminal velocity. Um, Hopefully you guys have heard of this term before, terminal velocity. So terminal means the final, because terminus means the end, right? So terminal velocity means the ending velocity. So if something has been dropping in air for a really long time, it reaches terminal velocity, the final velocity that it can ever achieve. So So I don't. This is one of those problems where like they talk about in SPM or SCPM, but I think like I want to talk about it again because I want to give you guys a different perspective on this. So this thing has mg, and suppose we call the drag force kv squared lah, turbulent drag. So when you start out with zero drag, when you start out with zero drag, it's just mg, and then the drag force grows, then finally drag force is equal to like will be equal to the gravitational force. So um over here, I want you guys to think of momentum. So at the start, um the ball moves because it gains acceleration. Its momentum keeps changing because there is a net force on it. So in a sense, gravity is a source of momentum. So like gravity is a force, but I want you guys to think of gravity as a source of momentum. So gravity gives this ball like more and more momentum. So it's kind of like a momentum, um, like gravity has a constant momentum flux lah. And so um, when the drag force grows and grows, the reason why it stops accelerating is because the momentum stops changing. Even though gravity still exists, in all these cases, gravity still exists. It keeps giving the object momentum, but at the start, the momentum is used by the ball itself to accelerate, whereas in the end, the momentum itself is given away to the air particles that influence the drag. So it's kind of like the process changes. Like at the start, the momentum goes to itself. The additional momentum gets absorbed by the object, and then like it keeps evolving, and then finally in time, at its terminal velocity, um, all the additional momentum it gains from gravity, it gives back to the drag force, to the air molecules, the particles, to things causing the drag force lah. It gives the momentum away to that. So this is why um there would be well there will be no net force in the x and y direction because there's no sources of momentum in x and y. I know it's quite straightforward to say, but like yeah, whenever you want to think of a dynamics problem, you can think of it in terms of momentum, because that's quite it's quite a good perspective to have in your mind. Um, yeah, so I think a small interjection. Okay, now let's move on to okay, again, any questions so far? If you do, here's a great place to talk about it. Okay, rotations. So now we talk about rotational dynamics, which is a little bit funky. So, um, recall last time when we talked about kinematics, we used the right hand rule. Um, was it here? No. Yeah, here. Um, use the right hand rule to define you use the right hand rule to define like the direction of angular acceleration, angular velocity, and related objects. But so if you have something in circular motion that rotates, this will be the angular velocity, um, whose direction is dictated by the right hand rule. So yeah, last time we talked about this, we talked about the angular displacement, angular velocity, angular acceleration. But now we want to talk about an angular momentum. So angular momentum is similar to momentum. So remember P is equal to m times v. But angular momentum is is r cross p. So it builds on the idea of momentum. It builds on the idea of momentum. So what does r cross p mean? So suppose you have this point here. Suppose you have an object of mass m rotating. Actually, no, wait. Suppose you have an object of mass m like in a circular motion around this axis. So the black line is just its orbit. It's not anything. The black line is just a trajectory. So you would see that this is r, this is p. Just imagine that like it's in the page. Um, Let me just draw it again. There's RP, and so our cross P would just point out of the page. And this will be L, out of the page. So you use your fingers in the R direction, cross it to the P direction. That direction will be L. So, okay, yeah, so that's the fundamental building block of angular dynamics. And then there's also a Newton's second law variant. So initially, we have the sum of forces being equal to dp vp. Now, if you cross, assuming that r is constant, um, which it might not be, but we're doing some suspicious math here, but it's okay. So you see that this is just a torque. And on the right hand side, it's an angular momentum. So that's also a Newton's second law for the rotational system. Um, it's related to the cross products of r cross something. Um, right. So I think the reason why rotational systems are so unintuitive is because of the cross product. I think cross products are just not built into the human operating system for some reason. Um, which like fair enough because like we don't live in a world where we need motion in the z direction. Um, because like when things move in XY direction, like why would you think of it in the z direction? But then again, that's what builds on rotational dynamics. The whole of rotational dynamics builds on um, this axis here, the axis perpendicular to the direction of motion. So yeah, whenever you do a rotational system, always think of where the axis is and where angular velocity points. Um, One thing to note, it's really tempting to say that, oh, sorry, before that, one more thing that I forgot to, sorry, it's really tempting to say that since P is equal to mv, therefore L should be I omega, where I is some rotational variant of the mass. So this is what we call the moment of inertia, and it's basically just mass. It's basically just math. It's basically just math, but like there's a few nuances to this. Um, it is true that you can write this equation, and it will be a right equation, but it's not as simple as you expect. So it's not just L equals I omega. As in like I is sometimes it might not just be like a scalar because over here P and V point in the same direction, right? P and V point in the same direction. If something moves here, P also moves here. So that's so therefore you can always write P equals mv where m is just some number. But in the rotational world, it's not always true that it's a number because L and omega might not be in the same direction. L and omega might not be in the same direction. So it's kind of weird to say this, but so moment of inertia, you can't take it as a vector, you should take it as a matrix in the most general sense lah. But I think for most problems, where there's not a lot of sus things going on, for most problems, the moment of inertia is just a number. So in this case, moment of inertia does indeed point in the direction of omega. So in this case, it's okay. Let me show you a weird case. So a weird case is um actually no. I think I'll just for the interest of time, I think I'll like because I'm gonna be sending out a handout anyways. But in the handouts, there's gonna be this example where you will see that L and omega might not always be in the same direction. Yeah, I just realized we're running out of time, so let's move on. But yeah, like I will say that this is not always true. It's a matrix, and if you know what matrices do to vectors, matrices bring vectors somewhere else. So like they might point in a different direction depending on the system. But yeah. Okay, so what's next on the agenda? Okay, so that's angular velocity. Okay. Um. So one more thing is that I think wait, I don't think we talked about this last time. No, I don't think we did. Yeah. So something else that we didn't talk about last time was how you could solve static problems like equilibrium. So um when something's equilibrium, it's not moving, it's not rotating, right? Um. So suppose some object is being acted on with like forces, 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 forces. So if something is in equilibrium, the sum of forces is zero, and so is the sum of torques. It doesn't accelerate, it doesn't rotate. But now there's a question like, where do you measure this torque from? The torque is always from an axis, right? So the key idea here is that in the statics problem, when this is true, it means that it doesn't really matter where you choose your axis. It doesn't matter where you choose your pivot. The axis can be arbitrarily chosen. So why is this? So since sum of torques is just R cross F, um, if initially I choose this as my origin, and then suddenly I choose this. So I'm just choosing two random points right now. I'm just choosing two random points. So if I choose this point, then there's a shift, right? The origin shifted by a little bit. We call this D. So and then so now like if you want to describe forces, you have two origins. You can describe it with this origin, or you can describe it with this origin. So that one force, the one force I'm like pointing to right now, you can describe it in two ways. You can describe it relative to the origin, which we call R, or you can describe it um, with this new vector here, R cross R minus D. Yes. So now you can also write like Ri. So since Ri is just oh, okay, wait, sorry. So suppose I want to describe the torque in a new system. If I want to describe the torque around this point, if I want to describe the torques around that axis passing to that point, so it'd be Ri minus D cross F, and that would be Ri cross F minus D cross sum of F. And since in the statics problem, this is zero, therefore, this is also just torque around another point. And so notice that D doesn't doesn't play a role here. Anything that has a D kind of gets cancelled out in this in the grand scheme of things. So in the statics problem where all the forces are zero, you can always choose any random pivot. Choose any pivot that you like. Choose any pivot that's convenient. So yeah. Um, One last thing. Well, actually two last things. So is that okay for everyone? Well, like one and a half things. So um, so Chas. Oh, I okay, cool. Chas theorem, or Chasles. I've never knew how to pronounce this. Chalet's theorem. I know. This guy's theorem says that any motion in the world can be decoupled into this. Any motion in the world can be decoupled to, sorry, can be decoupled into this. So what does this mean again? Sorry, let me just step back a little bit and describe this. So Michelle's theorem says that like any if you have a system of particles, can be what can be these guys, and these guys like move and rotate. Oh, but things running low on battery. But like if you have a system of particles or like a rigid body, for example, if you can also talk about um let's say a wheel rolling on the floor. That's also a system of particles because a wheel is made up of like many discrete particles, right? Like, there's atoms and stuff, so like, you can say that a wheel, like you can break it down into like many infinitely many particles. Um, but the point is, if you want to describe some like one thing in this system, suppose okay, let's just use this wheel example. Suppose this thing not only rotates, so like okay, suppose this thing not only rotates, but it also translates through space. So it might not be rolling in the direction of it might not be traveling in the direction of rolling. Um, but suppose it's like something floating in space lah. So imagine something floating in space. It's just like going, it's flipping around like a screensaver. Um, so you could describe any point on this. So it's kind of complicated, right? Because suppose you follow this one point. So suppose this whole thing goes over there. So suppose you follow this one point. You'll get that this thing would like do something like this, right? Because that point rotates but also translates. So Shell's theorem says that you can decouple this motion always into two, which is to say that when something translates and rotates, you can treat it as a translation plus a rotation. Well, it's straightforward, but like it's a great mathematical way to write it down. So the velocity of this point is going to be the velocity in the translation part. So this is translation, and this is rotation. Right? Is that okay for everyone? Um, like why this equation makes sense? So over here, omega would be pointing into the page. And R minus RCM is just relative to the center of mass. Like, where does this thing um, lie on? Okay, so we have something similar for angular momentum as well. So angular momentum, um, actually no, I think it's okay if you just like go read through the notes because a lot of things that I will say here is just in the notes as well, and I don't think it's too important. Um, but there's also a similar Charlotte's theorem for angular momentum. Um, but yeah, definitely do go read through that. Okay, I want to spend the last 30 minutes talking about energy. So energy is okay. So before we move on to energy, everyone, if you have any questions, just feel free. So okay, energy. Um, so energy is something that we all try to conserve. Um, so the building block for energy is the work. It's work. So work is not energy. Work is the change in energy. So energy, like the whole idea of energy is built on not having an absolute scale for energy. So we never talk about absolute energy. Oh, sometimes we talk about absolute energy style when you want to like simplify problems. Um, when you want to make things convenient, you can choose points to be zero energy. Uh, but yeah, no, but that's you true like you impose um a 0 point for energy. Anyways, my point is that like the whole building block of energy doesn't talk about the absolute scale. It only talks about the changes in energy due to forces. So if you have something that's moving, um, if you have something that's moving, suppose you have a box. The classic example is that you have a box. This force displaces the blocks. See, exert a force on it. This this box like displaces by delta x. Therefore, the work done on the box is F delta x. Well, that's true. But it's more like you can do more than just like looking at boxes and pushing them, right? So the whole idea of energy is that you can also split this up into infinitely many parts. And then you can say that the total change in work is just going to be the dot product with force and displacement. So it's a dot product. Remember, there's a dot product there. Um, so again, recall from like one of the first lectures that we had, the dot product. Uh, not sure where it is. Oh, maybe we did not cover it. I don't remember. Anyways, like the dot product means like how similar these two vectors are. Lah. So if the force is here, but the displacement is here, this might be because of constraint. This might be because of like other forces. Uh, so yeah, like if the force is not parallel with the displacement, you have to multiply by the cosine theta between them. So it's a dot product. Okay, so why is this useful? It's useful because once you know how a force acts as a function of position, you can basically know like how much energy it takes to get there. So this kind of force we call a conservative force. This kind of force we call a conservative force. Not because they support Donald Trump, but because they are things that are have a well-defined force at every position. So as in like when you come back to the same position, the force is gonna be the same. Um, so it's not a path-dependent thing. So suppose you want to talk about forces at every point in on the grid. So there can be a force here, force here, force here, force here, force here. And then maybe here it's like something like this. Lah. So my point is that like the vector field, the force field is just constant. Like it doesn't depend on the position. Like sorry, it depends. It can depend on position, but it doesn't depend on the path you took to get there. So suppose I start from here and make a circle. I come back here. The force is still the same. Then yes, this force is a conservative force. There are some cases where that's not true, especially in like electromagnetism, where there's EMF. But yeah, don't worry about it. Um, for now. So yeah, like for a conservative force, you can find the change in energy. So like So you can derive an equation for conservative forces, and these include like gravity, En, um, among other things. But yeah, as long as a force is conservative, you can always like derive gravitational energy, like electromagnetic energy. Um, yeah, so gravitational, so just energy in general. So how is energy useful? Energy is useful because like the change in like suppose a body gains energy. How does that impact like its motion? Because remember, like in the whole field of mechanics, we want to study how things move and why things move. So we have this how things move part already. We have this how things move part already from kinematics, but we want to like see what like why things move. So you could adopt the dynamics, like momentum approach, or you can adapt the energy approach. So here is to say that these forces can be any forces at all. Like it can be like literally what like whatever. Like they can be like friction, they can be like gravity, electromagnetism. So this at the end of the day, so you can write it two ways. You can write it in a way of like delta W. You can write it in a way of like the change in energy. Or you can say that the net force acting on the body is F equals ME, net force, sigma F, like the net force, not just individual Fs. So the total force can be written as dv dt on dot product with sorry, dot product with dx. So notice I combine these two things together to create velocity, and then from there I can integrate. This is just half v squared. So, suspicious. Half mv squared. Where have I seen that before? So that's just the change of the kinetic energy. So this is the work energy theorem. Um, the work energy theorem. It's important because like it's another way that you can look at dynamics problems. So what do I mean by this? So just by writing down you just feel wet. So this is just so this is another way of looking at dynamics problems, is to look at the energy. Um so oh fair enough. So right, so hold on, let me just because over here, this is when we broke down the forces into each individual component parts. So therefore we can talk about individual component energies. So for example, if you have a problem with gravity and EM, you can break out the energy into the gravitational energy and the EM energy. This should be intuitive. Um, Over here in the second part, what I'm saying is that the total change in work, the total change in energy, the total work done, would directly go into the kinetic energy. If it increases the total energy, then the kinetic energy will increase and the body will speed up. Um, However, you kind of lose this. So you kind of lose this one information. You lose this one piece of information of direction because, like in the work energy theorem. Sorry, let me just yeah. So it's the total work done is just equal to the sum of individual forces components of work done. So if a body yeah, if a body has like net positive work done, then the kinetic energy will increase. Otherwise, it will decrease. Otherwise, it will decrease the kinetic energy and stop it. Um, So like in the sense that this is good and bad in two ways. So like what I mean by this, if you want to do a dynamics problem that involves acceleration, this is probably not a good way to start. Well, actually, no, it might be a good way to start depending on like how much you know, lah, but this is generally not a good way to start. If you want to start a problem that involves velocity and speed, then yeah, maybe energy is a good way to start because so you can talk about the individual energies, sum them up, and see that that's equal to half v squared. Um, so yeah, because you know the v squared is the speed squared. So okay, that's the work energy theorem, the wet theorem. Um, let's kind of derive a few common energies. So spring energy. So spring forces are denoted by F equals negative kx. So so if suppose you were the spring. Oh, okay, so now it's a little confusing in this part, so I hope you guys can follow together with me. So whenever we say change in energy is equal to force dot product with the displacement, there's a sign convention here. You have to be careful with the sign. So over here, I chose a positive sign because it's like I am the person who exerts the force, and therefore this is how much energy I'm giving to the box. If you adopt the perspective of the box, if you adopt the perspective of the box, the force is being pushed on you. Um, if you know. Yes, sorry. Let me rephrase that. So, sorry, my bad. Let me restate that statement again. So this equation, this delta W is equal to F dot dx, um, is written in terms of the box, in terms of the box. So the box feels some force, it feels some displacement. The change in the box's energy would be the force times the displacement. In this case, when you have a spring force, this force is not so when you talk about this force, um, you can't just I mean you can just put it into here, but you have to be a little bit careful. This will be negative half kx squared. Just integrating directly. But yeah, I just want to be more like cognizant of the sign convention here. So the negative means that you're losing energy. Huh, how can you lose energy when you like pull springs? So the key here is to talk about whose energy. So if you talk about F equals negative kx, you're seeing that in this in the spring's perspective, the spring exerts this amount of energy. But to the box, because of Newton's third law, it's actually like flipped around. So um yeah, so so yeah, wait, is that good to say? Okay, well I think it's better to look at it like this. So you have a spring. Oh, that was a good spring. I should just use this. So the spring, um, how do I explain this? The When you stretch it to when you stretch the spring to some displacement x, uh, you are losing energy because you're like as an external observer, you're putting your hand in and increasing the displacement. So you are losing energy. Um, so that's why it doesn't negative there. I think Okay, okay, wait, okay, I realized now that I've like put this out, I think I've realized something that I do versus something that I like would like to like talk about in lecture, which is it doesn't really matter. Like just think of the sign convention. It doesn't really matter the details of all like like whose energy is it, like the god of hand coming in to like increase energy. What you should remember is to be cautious about this. What you should remember is to be cautious about this and like be be ready to like amend your equations. So what I mean by that is to say that if you have a negative sign, oh think about it, oh wait, I have a negative sign. Is this does this make sense? Is this for the spring or is this for the box? Um so yeah, because negative means a decrease, right? So like someone's energy is decreasing here. Whose is it? Because it makes sense, right? If someone's energy decreases by the conservation of energy, some other body might increase in energy. It might be so. This may be like friction, like energy loss to heat. It can also be something useful like gravitational potential energy. So you don't know, but the point here is that like when something has a negative sign, just like make sure like think about it. Oh, is this what I want? Sometimes people might slap on the negative sign here, but just just yeah, just be wary that like the negative sign comes from the different perspectives. This negative sign here comes from if you have a hand from external from the outside, you pull the spring, that's how much energy you would exert. So let's see. Maybe gravitational energy. Okay, so delta W will just be the integral. Sorry, if I use the non-negative sign, so r hat dot dr is just dr. So let me just okay. So yeah, that's the change in gravitation energy. Um, so like I just kind of like went non-verbal and like did all the math, but let me just explain what I did. So Newton once said that that was his force for gravity, and if you just like put it into um, the work, the expression for work, you get a dot product with the radial displacement. And so because like by definition, gravity is a radial force, so it would dot product with this and just give you dr. And so negative dr over r squared, you can write as like change in 1 over r. Um, and so finally you get like gmm over r. If you've done like gravitational problems before, you might be like, oh no, wait, this is missing a negative sign. So like, so this sign convention thing comes up again. So you have to be cognizant of like whose energy you're talking about. So if you're talking about um like some object that you come in, you use a hand to like pull it to infinity. Um, or like when you're talking about some object where you come in and like increase its gravitational energy, what what you would do is this: you increase the gravitational energy by this much. Um, so you gotta think about like which hmm, you gotta think about like what system has more energy and what system has less energy. So for the spring example, if this is the equilibrium point, if this is the equilibrium point, then this would like then this extended length would have more energy, and therefore like when you extend it, it should be a positive sign, not a negative. Over here in the gravitational world, sometimes it has a negative sign. Why is it? So in these cases, like it's best to think of like what's happening in the real world. Like instead of just like having your head in the math, think of what's happening in the real world. So in the real world, this system on the bottom has more energy than this system, right? This system here has more energy than this system. Why is that? When you release, so when you're holding these two in place and then you release it, they will like collide with each other, right? But since this situation has more like when they collide, they collide with more velocity. Therefore, the system on the bottom has more energy. Um, so when you have a higher R, potential energy should increase. When you have higher R, potential energy should increase. Um, Therefore, there's a negative sign here that we missed. Because Gmm over R, if you increase this, the whole thing decreases. But if you slap a negative sign on it, the whole thing increases. So it's kind of like this, the systems are getting like less and less negative. So this, sorry, not very. All right, so just imagine this. So like there's no mathematical way to I mean I'm not using a mathematical way to express this. Um, but I'm just like seeing by intuition. By intuition, if you have a larger separation, then when they collide, these two things are gonna collide more violently, right? Like because they 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 get more velocity when they collide. They get more speed when they collide. So yes, if you tack a negative sign on it. Um, so there's a few ways like there's a few arguments that you can use like say oh if you it's that external force so externally you give the system energy that's why there's an increase that's why there's this expression of decreasing energy but just like think of the system and like slap a negative sign if you think if you think it's necessary. This is the more practical way of explaining this lah. Like you can be really like poetic and say everything about like external hand of God, um, and like inserting energy into the system, absorbing it. Like don't worry about it. Just slap a negative sign if you think it's necessary. So therefore, U is negative W graph. So this will be the gravitational potential energy. And so over here, same thing for the spring force. Okay. One more thing. One last thing that I want to discuss is that the conservative force criterion. So this is just a sanity check. Just a sanity check. Like, are these forces conservative? So remember what our definition for conservative is? Conservative means that it doesn't depend on the path. A force just is at every point in space. So at this point in space, you have this force. At this point in space, you have this force. So yes, these two forces are conservative. They have well-defined vectors at well-defined places. So yes, these are conservative. Um, let's see. Let's see. I will try to go through one more problem. Um, maybe I think it's okay. I think you guys can go through problems on your own. Because I think yeah, time is would be better spent if I just ask you guys if you have any questions right now. Um, So yeah, if not, then I guess that's a great place to end tonight's session. So thank you for coming. Handouts will be posted, recordings too. And yeah, see you guys next time. I think next week we'll be having Yongsheng give a lecture on waves and oscillations. So like do stay tuned for that. You can finally stop hearing me yap. Then yeah, Yongsheng will be taking over for the next few lectures, and then I'll come back afterwards. But yeah, thank you for coming, guys. Have a great day. Bye.